Okay. Thank you, those of you who are here, for braving both the rain and the iodine. The rain actually is good because it keeps you all indoors where you don't get radiation poisoned. Okay. So today we're talking about a topic that's not in the book. And the reason we're doing it is that the 61B instructors want you to have seen it before you do 61B. And what we're looking at, this is kind of the big picture here. We have the abstract notion of a sequence. First element, second element, third element, and so on. And two different ways to implement it. The way we've been talking about up to now is the list, where we link pairs together by their couters and have the cars point to the elements. And this new way is called a vector. In other languages, it's often called an array. And it's a bunch of locations in memory that are right next to each other. So there's no link, there's no couter linkage. It's like just a bunch of cars, in a way, in a big block. Abstractly, they behave exactly the same way. Abstractly, they're both sequences. And you can do everything that you can do to a sequence with either one. Different things turn out faster depending on which one you use. So let me talk about the similarities and differences. Well, no, let me not. Let me start by showing you a little bit about how vectors work. So I'm going to say define v1 to be make vector 4. And here's the value of v1. The first thing to notice is this number sign right at the front. So number sign and then stuff in parentheses means this is a vector. So the notation is parenthesis, element, 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 close parenthesis, just like a list. The only difference is that number sign at the beginning. The standard does not say what the initial value of those elements are. In STK, we have this funny thing called number sign unbound, meaning we haven't given this element a value yet. I could also have said, if I want, define v2 to be make vector for, I don't know, the empty list. And then v2 would be a vector containing 4 empty lists. So let me back this up so you can see both kinds. So make vector takes an optional second argument, which is the value to put in all the elements. If you pick a non-empty list as the initial value, which would be unusual, you should bear in mind that all of these elements are going to start out EQ, not just equal, because we take the very same thing and stick it into every slot. So with lists, you don't say ahead of time how big the list is going to be, right? You can just const things onto the list forever. With vectors, you do say right at the outset, I want a vector of this size, and that's how big it's going to be forever. And that's a consequence of this picture. The scheme system has to allocate a chunk of memory that's a particular size. And there might be something else right next to that block of memory, so it can't just grow and shrink. So that's a very important difference. Vectors are really good in situations where you do know ahead of time how many elements. So the example like x, y, and z coordinates for a point in 3 space. You know, and it's always going to be exactly 3 elements. Okay, now that I have this vector, what can I do with it? Well, I can say vector ref v1 2, let's say. That's unbound. And if I set it for v2, I would get the empty list. in scheme, the elements of a vector are numbered from 0. So these vectors have elements number 0 through 3, and there is no element number 4. So if you want to know the position of the last element, it's the length minus 1. And I can say vector setbang v1 to, quote, foo. Now if we look at v1, we'll see that element number 2, which is the third element, has the value foo. Okay? Very commonly, what you have is a vector of numbers, and you give them the initial value 0, and then you're counting something rather than you add 1 to each one. Is that a hand up? No. Okay. Okay. So the main constructor for vectors is make vector, which is very different from anything for a list. There's no make list of size n. What there is, however, is there's the procedure list, and there's similarly a procedure vector, as opposed to make vector, that takes any number of arguments and returns the vector of those elements. So that's something that is kind of the same as how lists work, but these are derived procedures. In chapter 2, you learned how to write lists using cons, and the same thing is true here. This vector procedure is implemented using make vector. Yeah? Can you quote a vector? Yes, you can say quote, number sign, and then whatever. Okay? Just as for lists, you're not supposed to do that if you're going to mutate it, which you always are for vectors, right? Vector programs, it's very rare to see a constant vector that sits around forever. Okay, so vector ref, which we've already seen, works just like list ref. The difference is that list ref is not one of the central selectors for lists. It's implemented using car and coder, whereas vector ref is basically the only selector for vectors. It's the primitive selector. For vectors and lists, we can ask how long they are. Length is, for lists, implemented by codering down. Vectors just know how long they are. Each vector has like a header that contains that information. And then here are the things that are different. There's nothing like cons, car, and coder. There's nothing like make vector. There's nothing quite like set car and set coder, but there is the mutator vector setbang, which is different in that it takes not only a vector but a number which says which element do I want to change in the vector. Okay? Questions so far? Okay. Up at the top of the screen, here, let's make this a little smaller. There we go. Up at the top of the screen is map for lists. You've seen that a million times before, so I'm not going to go through it, but it's just there for contrast with vector map implemented below it. So vector map takes a function and a vector, and it returns a new vector in which we've applied the function to each element of the original vector. So unlike regular map, vector map has a helper function, and then here's the call to that helper. So this is the actual body of vector map. And before we get into the loop procedure, the very first thing we do is make a new vector in its entirety whose length is equal to the length of the argument vector. Okay, if we were trying to do vector filter, it would be a lot more complicated because we don't know ahead of time how many elements would satisfy the predicate. So we wouldn't know how big to make it in advance. But for map, we know that the result vector has the same length as the input vector. So here we are making this vector, and in the loop procedure, it's going to be called new vec. That's a formal parameter. And the other argument that we're giving it is vector length of vec minus 1, which is the index, the element number, that's called an index, of the rightmost element. I wrote this procedure going right to left through the vector. You could just as well do it left to right. I find this a little bit easier because the end test going right to left is n equal to 0 rather than the longer is n equal to vector length of vec minus 1. Less than n0. Sorry. It would have to be greater than vector length minus 1 or equal to vector length. It's less than n0 because 0 is a perfectly good element number. It's only when we get down to n equals negative 1 that we're finished. So if n is negative, we're finished. Just return new vec. New vec started out having unbound as all of its elements, but you'll see that by the time we get to the base case, we've filled up each slot with the new value. So if n is a valid index number, then we do this. I think you've seen begin before in other contexts. It has any number of, it's a special form. It takes any number of expressions, evaluates them left to right, or top to bottom in this case, and returns the value of the last one. So in this case, there's two expressions. First one is vector set bang, new vec, element number n, to fun of vector ref, the original vector n. So we take element number n, call fun on it, and put it into the same slot in the new vector. And then we call loop recursively. This is a tail call, by the way, so this is an iterative process. With new vec being the same vector, it's not cdr of new vec the way it would be for a list, but the new index is n minus 1. So we work down to 0, which is the leftmost element, then negative 1, and that's when we return new vec. Is that a hand up? Yeah.
Why didn't you make a new vec instead of just using vec?
Why did I make a new vector instead of just using vec? Because I like functional programming. And even though we're dealing with vectors, I still would rather leave my old one intact. Just because this is a very general procedure, right, that you put in a toolkit. Maybe whoever calls vector map is finished with the original values after the call to vector map, but maybe not. So I would rather leave the user with that choice by returning a new vector. Okay? You can write, and people do write, vector map bang, that does what you're saying. Just replace the values in the original vector. And that exists also. Okay? Other questions? Cool. Who's programmed with arrays before? Some have, some haven't. Okay. So this is worth doing. Okay. That's vector map. Okay. Why would we want to use vectors versus lists or lists versus vectors? And the issue has to do with certain things are fast with lists and other things are fast with vectors. It's just efficiency. Like mutation altogether is just about efficiency. So there's a chart over there on the third board. The place where vectors definitely win is if we want to look at the 100th element. For a list, we have to do 100 cdrs, or 99 cdrs, whatever. No, 100 cdrs, because we number from 0. We have to do 100 cdrs and then a car. So it takes theta of n time to find the nth element. For a vector, because they're all right next to each other, And these pointers that we represent as arrows in the diagram, each pointer is the same size. Given that we know where the starting point is of this vector, we can calculate where the 100th element is. So that's just a piece of arithmetic. Now start with the starting position of the vector and add 100 times however long a pointer is, and there's the 100th element. Or that's the location of the 100th element, and we can just look at that. So finding the nth element of a vector is theta of 1 time, not theta of n time. That's important if you're writing a program that sort of jumps around a lot. First we look at the 100th element, then we look at the 35th element, then we look at the second element, then we look at the 200th element, and so on. Where lists win is if we don't know the length ahead of time, and so we're going to write a program that builds up a list element by element, or builds up a sequence element by element. That's easy to do and fast to do with lists, and very hard and slow to do with vectors. So for a vector, if you have a vector of length 5 and you now want to add a 6th element, you have to create a brand new vector of length 6. You can't say make my vector bigger. You have to make a new vector of length 6 and copy over each of the 5 elements, ba-boom, 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 and then add the new one in the new position. So adding a new element to a vector takes time theta of n because you have to copy all the old elements. Whereas adding an element to a list takes time theta of 1. You say cons, it makes one new pair, and that takes constant time. I'm saying that with my fingers crossed. It takes constant time unless you run out of memory and the system has to do garbage collection. But it still takes constant time almost all the time. Another thing I'd like to point out is that the most common thing to do with a sequence, neither one is more efficient. And that is, look at the first element, look at the second element, look at the third element, the way we did with map and vector map. Both of those take time theta of n. It's only if you're jumping around in the sequence that vectors win. If you're going from left to right through the sequence, which is the more usual thing, then vectors and lists are equally good. So a lot of people are confused about that and think that vectors are just always better at finding things. But it's only finding things where you jump around. So my favorite example about this is writing a program that plays some kind of card game, Solitaire or 21, like the project or something. The first thing you have to do is make a deck of cards and shuffle it. Shuffling a deck of cards is a great example of something that's best done with a vector. Because the way you shuffle a deck is you pick a random number less than 52, and you interchange that element with element number 0. Then you pick another random number less than, well, all right, let's exchange it with element number 51. That makes it easier. Now take a random number less than 51 and interchange that element with element 51. So because we're picking a random number each time, we're jumping around in the deck. That's what it means to shuffle. You want it to come out random. And so vectors are really good at that. Now we've finished shuffling. We have this deck. And let's say we're playing solitaire. How do you play solitaire with a deck of cards? Here's the deck of cards in probably your left hand, but I'm left-handed, so it's in my right hand. And you go vroom, chung, chung, flung, flung, right? Vroom, flung, 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 flung. One card at a time moves from your hand to a pile, one of the 7 piles, right? That's much easier to do with lists because the card that I'm moving is car of the deck. What's left in my hand is kutter of the deck. And the new pile, after I've put that card down, is cons car of the hand onto the old pile. Okay? So writing a program to deal out the cards is much easier with a list. So much so that when I write such programs, I actually convert between list form and vector form. I shuffle the deck as a vector, and then I call something I didn't write on the board. Vector to list of V. This is a minus sign followed by a greater than. It's supposed to look like an arrow, and it's pronounced to, as in vector to list. And there's also list to vector L. That does the obvious thing. Okay? Don't fall in love with those conversion procedures. In particular, in the next midterm, when we say, write a vector program that does such and such, don't say vector to list, and then blah, 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 and then list to vector. 0 points. It will say that on the exam. But for situations like, they're special, like this deck of cards thing, it really is useful once in a while to be able to convert. What's the order of growth of the conversion? How much time does it take? Yeah, it's theta of n both ways. Because you have to visit every element. It's like the last row of my table there. You have to visit every element in order to do it. List to vector, you have to start by finding out how long the list is. So you're going to probably end up traversing the list twice. Whereas vector to list, you know how big the vector is, and it doesn't matter anyway, because you're going to cons one element at a time. When you write vector to list, are you going to go through the vector left to right or right to left? And why? Yeah. Yes. Thank you. The only right way to do it is right to left, because for each element, you're going to say cons this element onto the list I already have. And so the one that you cons on last in time is going to end up being the first element of the list. So you should start with the last element of the vector and work your way down to the first element of the vector. Okay, good. I'm always terrified to show this to people, because some people think it's meant to be a good idea. This is something you shouldn't do. I'm just showing you that it's possible and why it is that it's slow. So this is vector cons. Nobody would write a vector program this way. If you find yourself wanting to use vector cons, you should have been using lists in the first place. Or you're not thinking about your vector program properly. So what I want to do is I have a vector, and I want to stick a new value in front. So I'm going to start. All vector programs basically have this structure with a little inner loop. I'm going to start by making a vector that's one bigger than the vector I was given. Okay? And I'm going to start with an index that's vector length of vec, not vector length of vec minus 1, the way it was last time, but vector length of vec because that's the rightmost element of the new vector. The new vector has vector length of vec plus 1, so its rightmost element is vector length of vec. So here's loop new vec n. And we start out, this time the base case is n equals 0. We'll see why in a moment. But let's start with n being big. And we're going to do this begin here. Vector set bang new vec n. So put into the new vector. Vector ref vec n minus 1. So let's say we have a vector of length 5, and now it's going to be a vector of length 6. So we're saying vector set new vec 5, vector ref vec 4. Element 4 of the old vec becomes element 5 of the new one, and so on down. Then we loop with n minus 1. Finally, when we get to 0, we're not copying from the old vector anymore. We're going to vector set new vec 0 to be this new value here, the thing that we're trying to cons in front. So that's what we stick into slot 0. And then there's no recursive call. This is the base case, and we just return new vec. Right? So how long does it take to do vector cons? Theta of n, because we're going through the whole vector, copying things over. So again, don't do this. This is just to show you why you wouldn't want to. Is that a hand up? No. Everybody's sort of doing this today. Maybe it's a symptom of radioactive iodine poisoning. Okay. So I talked about shuffling. I have a few different shuffle procedures in lecture notes. So the first one is, here's how we would do it just with lists functionally. So I have a list and I want to shuffle it, get it in random order. I'm going to say, here's the body of the procedure after that inner definition of loop. It says, if the list is empty, then return the empty list. There's nothing to shuffle. There's only one ordering for an empty list. Otherwise, we call loop list, the old list, empty list. We're going to build up a new list on top of that, and a random number less than the length of the list. Okay? And then there's this loop which does something awfully complicated. Let's say n is not equal to 0. So we have a list of length 100, and our random number was 5. So we call loop coulter of n. So one fewer element in n. Oh, I'm sorry. No, that's if n equals 0. So if n is, no, it's not. If n is not equal to 0. Wait, is this backwards? Wow. Has this program been wrong all these years, or am I losing my mind? Let's see if it works. Yeah, it works, so it must be right. Okay. So if n is not 0, we remove the top card from the deck. We add that top card to out. Oh, I see. Out isn't really out at all. That's what's confusing me. It's a very complicated program. I should rewrite this. Out is a sort of holding tank, because we picked a random number. We picked 5. So I want to get down to card number 5. So what I'm going to do is take the first 5 cards of the deck and put them in a separate pile, which is called out. So I use coulter to remove the card from in, and I cons that card onto out, and I make a recursive call. I keep doing that, transferring cards from in to out, until I've transferred n cards. So the n plus first card is element number n, because we count from 0. And so now I have car in being the element I want. So what I'm going to return is cons car in onto a recursive call to shuffle, appending coulter in without. So the transfer from in to out sort of has no particular meaning, because once I found that card I was looking for, I'm going to smush the two together, and they're not in any particular order anyway. They're the ones that haven't been shuffled yet. And now I'm going to call shuffle 1, not loop. Notice that that's the important point that I missed first time around. This call is not a call to loop. It's a call to shuffle 1. So we take every card except the one I just picked, shuffle them randomly, and then stick this card that I picked randomly at the front. So that's the shuffle algorithm. How long does it take? Why? Yeah, moving some element to the front takes that element's index number of operations. Okay, the index on average is half of the size of the list. So n over 2, which is theta of n operations to find that card. And then we have a recursive call to shuffle for all the rest of the cards. So it's order of n for each card, and there's n cards. So it's order of n squared time to do this shuffle. So that's pretty bad. I'm not even going to look at this. Shuffle 2 bang is just to show you that even with list mutation, it still ends up taking n squared time. So you can read that on your own. I don't like it, even though I wrote it. And we'll move right along to shuffle 3. So now we have as a vector that we want to shuffle. So we call loop, vector length of vec, which is one more than the rightmost element number. So what does loop do? If n equals 0, never mind that yet. Otherwise, let index be random n. And this is why we used vector length and not vector length minus 1. Because random n returns a number between 0 and n minus 1, which is just what we need to get a random index in the list. So index is the random number. Temp is the rightmost element of the vector. So I pull out the rightmost element of the vector. We're going to do a swap. That's why I'm doing this pulling out into temp. I think when we talked about set bang, we might have gone through this, that if you're trying to exchange two things, you can't just say, set the first one to the second one, set the second one to the first one. Because if you set the first one to the second one, you've lost the old value of the first one, and now you're going to have two of the same thing. So you have to say, save the first one in temp, move the second one to the first one, and then move temp to the second one. And that's what we're doing here. Temp is the value that's at the right end of the vector. Index is a number between 0 and 1 minus the length of the vector. Now I can say, set that last element, the one I pulled out into temp, change its value to vector ref vec index. Index is the random number. So pick a random element, stick it in the end. And then vector set bang vec index, which is that random position, to temp, which is the old value from the end of the list, end of the vector. So I've swapped two elements of the vector. How long did that swap take? Theta what? Constant time, theta 1. That's the advantage of vectors. I can go to a random element in constant time. The whole thing is going to take, the shuffle is going to take theta n, because we have to do this loop n times. Because right down here we say loop n minus 1. So the entire shuffle takes theta n, whereas for the list it took theta n squared. That's a big difference. How much is 50 squared? 52 squared. Let's say 50 squared, it's easier. 2,500, right? So the difference between 50 and 2,500 is worth thinking about. Okay. If n equals 0, we're finished. Just return vec. That's easy. What if the random number that you pick is n minus 1? So we're interchanging the last element with itself. That's fine. No problem. And it's the same thing. All of these vector sets are setting the same value into different places. Not a problem. So that's how we shuffle a vector. Questions? Could you write this program on a closed book exam? Not that we're going to ask it, but suppose we did. There's two parts to being able to write this program. One of them is understanding how vector programming style works in general. And pretty much without exception, it's the body of your procedure is called a loop with an index and maybe a new vector that you make. In this case, it's shuffle bang. We're shuffling into the same vector. If I wanted to do a shuffle that made a new vector, I could do that, make a copy of the vector, and then I wouldn't even need this temp thing. I could just put things down in random places. Put random things in place, boom, 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 in the new vector. Yeah? No. Random n returns a number from 0 to n minus 1. Yeah. Okay. How is random written in Scheme? Well, the Scheme standard does not have random in it at all, I believe, although the next one will. So I can't give you a definitive answer to that question. So here's a little potted 5-minute lecture on random numbers. There are two ways to get random numbers. One of them is truly random numbers, which means that the value is somehow determined by quantum effects. No, seriously. And the other is what's called pseudo-random numbers, which is what almost everyone does. So the way you get a truly random number, for those of you who are electrical engineers, you will remind me that the voltage drop across a diode is 1 point something volts. Is that right? Who's an electrical engineer? Okay, all the electrical engineers are too wimpy to brave the rain. Or maybe they really know about radioactive iodine and we don't. Anyway, the voltage drop across diodes is always the same amount plus or minus a teeny bit. So for purposes of this discussion, I'm going to pretend that I know that it's 1.4 volts. So the real answer is somewhere between 1.399 and 1.401. Okay? So you take a diode, you get a very good voltmeter, you measure the drop across that diode right now, you subtract 1.4, and that gives you a random number. Okay? So that's how you make really random numbers. The way you make pseudo-random numbers works by things about the properties of integers. So you take a course on number theory, which is the mathematical study of the integers, and you learn about algorithms that spread out values pretty well. And what you do is something like this. You start with what's called a seed, an initial value. You get that not by always picking the same value. That would be bad, because then you'd always get the same sequence of random numbers. Instead, you take the time of day in milliseconds and add to that the angle at which your disk is spinning right now. How far along a rotation is it? And that kind of thing that is sort of more or less random. And you mix all those things together and you get an initial seed. That's your first random number. Now, by the way, random takes an argument, n. So what you do is you take your random number, divide by n, and you return the remainder. That's how you get a random number in a particular range. Now what you do is something like, and this is not the best possible algorithm, but it's an okay algorithm. You multiply your random number by itself. As you remember from elementary school, when you multiply two 4-digit numbers, you get an 8-digit result, right? You take the middle digits of the answer. So in computer binary terms, you have a 32-bit value. You multiply it by itself, you get a 64-bit value. you drop the first 16 and the last 16, you take the middle 32, and that's your next number. Okay? The algorithms they really use are more complicated than that, but that's a simple example. That particular kind of random operation, although it's very, very standard in computers that that's how they do it, it's not very good. I remember really having my eyes open about this when I happened somehow to web surf to an online gambling site that was advertising the quality of their deck shuffling, of their random numbers. And they pointed out that the number of ways in which you can order 52 cards is greater than 2 to the 32nd power. So if you take the usual computer 32-bit random numbers and you use that to shuffle a deck of cards, as in this procedure, you don't get every possible deck shuffling. You only get a few of them. And clever adversaries can figure out how your random number system works and which deck shufflings you're going to get, and after the first few cards come out, can predict what the rest of the cards are going to be. So if you want a good, fair game of cards, you need a better random number generator, namely one that generates wider random numbers. So there are standards in the world for how to get, you know, a 100-bit wide random number and so on. And they're a pain in the neck. Does that answer your question? Okay, good. All right, back to vectors. Okay, so in order to write this program, that was what I was talking about. There's two things you have to understand. One is the general characteristics of all vector programs, which is there's going to be a loop that counts the index either up from 0 or down from length minus 1 or something. And maybe there's a new vector, or maybe you're modifying the original vector. And then in your loop, there's going to be vector ref, things like this, vector ref, vec index, and things like this, vector set, vec index, something or other. Okay, and that's what's going to happen each time through the loop. So every vector program that you write should look like that. Now, in order to write a shuffle program, you have to know a good algorithm for shuffling a deck. It's not obvious how to do that. A lot of sort of first try algorithms for shuffling decks, certain outcomes are more likely than others. So like, you know, cards near the front tend to stay in the front, or vice versa. This is the correct algorithm. How do you know it's the correct algorithm? Because at home you have the, as of like a week ago, 4-volume series, The Art of Computer Science by Don Knuth. And you look up in, I think it's volume 2, shuffling. And you look at the algorithm, and he tells you what it is, and then you code it. That's how. You don't get to bring Knuth with you to the exam, however. So I wouldn't ask a question quite this hard. And not that this is hard, but it's a little bit tricky to get a good, fair shuffling algorithm. Okay. Oh, yeah. So just a brief comment on how this all works. In the computer, there's this memory, which is a huge bunch of what's called addresses. The word address is a metaphor for, you know, your street. The street you live on has, you know, number 1 Main Street, and number 2 Main Street, and number 3 Main Street, and number 4 Main Street, and so on. So each house has an address. And the addresses are, at least in principle, consecutive numbers, although sometimes they're not for various reasons. but in a computer, they are consecutive numbers. And the computer hardware lets you say, tell me what's in memory address such and such. Software uses that capability to build a storage allocator. This is one of the things you're going to learn how to do in 61B, is write a procedure that you call it with a number that's how big a block of memory you want, and it returns a pointer to a block of memory that's available for your use that's that size. Memory management is a little bit tricky because what happens after a while is here's memory, and somebody asks for a block this size, and then somebody else asks for a block that size, and then somebody else asks for a block this size. And now this guy in the middle says, OK, I'm done using this block, so return that to the memory that's available for anyone to use. And then a little bit later, someone comes along and asks for a block of this size. And it gets allocated here. And now what you have is this tiny little sliver of useless memory. Right? So that's what makes memory allocation complicated. And one of the nice things about lists as an implementation of sequences is that all pairs are the same size, right? They all have 2 pointers exactly. And when everything's the same size, you don't have this what's called fragmentation of memory. So that's a nice feature of pairs. Vectors, however, the reason you have to say how big it is that we're going to allocate a chunk of memory all at once to hold it. Once you have that thing, if you want element number 100, this is just simple arithmetic. So this block here is at memory location 1,000. A pointer is 4 bytes long, typical. I want element number 100. I take that number 100, I multiply it by 4, which is the size of a pointer. I get 400. I add that to 1,000, then I get memory location 1,400. I say, give me the pointer at address 1,400, and there it is. So that's why finding the nth element is constant time for vectors. Whereas with lists, the pairs can be all over the place in memory, because people are constantly allocating and deallocating pairs. And you never know where they're going to end up. So you have to go coulter, 100 times to find the nth element. All right. I'm not going to ask you questions about what I just said about how memory works. That's 61B material. I just want you to, if you're interested, have a clue about it. One last question? Everybody's scared to ask the last question. It's like the last cookie. Yeah? OK, why not round up the size to a power of 2? You can do that. That's one of the ways of doing memory allocation, to avoid fragmentation. Yes, that is a way. It turns out even better from a fragmentation standpoint, but more complicated to implement, you can look it up in Knuth, is rounding up to the next higher Fibonacci number. It's really weird. It's a very strange algorithm. Anyway, yes, so there are ways to improve the fragmentation problem, and you'll learn all about them in 61B. OK, see you next week, if you haven't died of iodine poisoning.